In this set of lectures, we're going to talk a little bit more about the Fourier series, and specifically we're going to talk about approximation of functions using trigonometric polynomials, at first discussing specifically the Fourier sinusoidal and cosinusoidal series. So Fourier series are sometimes used in approximation theory, and basically this is done by taking a partial Fourier sum. So in other words, in the Fourier series, instead of running the sum from n equals 1 to infinity, we run the sum from n equals 1 to some value capital N. And now f is a function, any function, and the only stipulation is that we must be able to represent this function f on some interval L. So by the Fourier series. So f of x is our actual function. Now, approximation theory says that there is some function capital F that's the best approximation for lowercase f, and that can be found by minimizing the square error. The square error is done literally on the integration of a continuous function basis, where we take our exact function little f and our approximation big F. We take the difference, we square it, and we integrate over the region. So we previously said some interval L. In this case, our interval would be obviously 2 pi. So this function f of x, we're going to use capital letters here, and so you can substitute in big F and little f, and if you do that, then you basically get an expression that gives you the error. And so the error is basically our function f minus the Fourier sum approximation. And I just want to point out here, it's a little bit confusing because your textbook author does, and he does this often, he's basically done a change of variables. So in the previous slide and in the first part of this section, the little a's and little b's correspond with little f. In this part of the chapter, the little a's and little b's correspond with big F. So this second part of the function here represents our function f, that is our Fourier series approximation. And so here's a graph below that illustrates how we might do this. The solid curvy line is our function little f, that's our exact representation, and then the dashed line is a Fourier series approximation of that function. So you can see that there's some error here in this vertical drop in that function from one period to another, or from one point to another. That's not perfectly simulated by the Fourier series, nor is the curvature. But this is what such an approximation would look like. And obviously the error would be the difference between each point integrated across the range of the function. So this leads us to a theorem that says the square error of f in this equation that has a fixed n relative to little f, our actual function on the interval minus pi to pi, is minimum if and only if the coefficients of capital F are the Fourier coefficients of little f. And the minimum error is given by the equation that we saw previously. So since the minimum error will always be greater than or equal to 0, and that's true for every value of n, then as n goes to infinity, we can write Bessel's inequality, which is stated here. So the left-hand side are the Fourier coefficients, and the right-hand side is the integral of f of x squared, normalized by 1 over pi, as long as, once again, the integral, this function f of x contains an integral that exists and has Fourier coefficients and can be represented by a Fourier series. So if you have then some function like this f, we can basically equate these two expressions, saying that we have Parseval's identity, and what's happened here is We have to be sure that the sum goes to infinity, because if it doesn't go to infinity, it becomes an approximation. Remember, Parseval's identity basically says that the sum of the Fourier coefficients squared is equal to effectively the total energy in the system, the energy in the system. So f of x would be like a voltage signal that's been normalized. Integrating then over a period gives us the power in that period. If f of x squared gives us the power, if we then integrate over a period, that gives us an energy in that period, and then this gives us the energy in the Fourier coefficients. So as an example, we can look at the minimum square energy in a sawtooth wave, and we're basically just computing for different values of n. So n equals 1 would be where you have basically just a pure sinusoid for your sawtooth wave. N equals 2 would be we have 2 terms in the series, and so on, all the way up to n equals 1,000. So here is, if we have n equals 20, here's an example of what a Fourier series approximation of that sawtooth wave looks like. The actual sawtooth wave would be a straight line from minus pi to pi. And so in computing the error, we basically need the equation for our function f. So the equation for our function f is the equation of the straight line from minus pi to pi that intersects the y-axis at pi. So here's our f in the parentheses here. We then square that and integrate from minus pi to pi over dx. And then we subtract the terms of the Fourier series. So how you would do this would depend on, exactly what you wanted n to be. So you would first do this integral, and then you would subtract this result based on your choice of capital N. And so here are some tabulated values where n is shown to go from 1 to 10, and then in increments of 10, and then up to 1,000. So this is giving us an estimate of the mean square error of the Fourier series that represents this function. If you look for small terms, the error is pretty significant. Then you notice that when you get to 6 terms, you've fallen by a factor 4. When you get to 10 terms, you're almost an order of magnitude lower. When you get to 100 terms, you're an order of magnitude lower than that. 1,000 terms, you're roughly an order of magnitude lower than that. So for this particular example, you actually have an almost linear change in your mean square error as a function of n. So pretty significant reduction of error to include more terms. Now, why do we care about this? A lot of times when we're analyzing waveforms in signal processing, we're concerned about the total energy in the signal. And so if you want to find out with a Fourier series how to represent the total energy in the signal, you need some idea of sort of where minimally accepted square error is. So that's just in this particular example, it's a little bit difficult to get physical meaning out of the numbers. And the reason is we're working with these 2 pi's and pi's. And so when we think of square error, sometimes it's better to have this normalized where you would go from -1 to 1 or 0 to 1 so that you have a feeling for how your error compares with the numbers. It's a little hard for me to think in terms of pi when I think of numbers. Okay, the other topic that we want to talk about here is Sturm-Liouville problems and orthogonal functions. So a Sturm-Liouville problem is typically a physical problem where we're representing some sort of oscillatory system. It's classic in its representation of vibrating strings, vibrating membranes, standing waves, and other similar problems. And it's represented by an equation of the following type, where P of x is some function of x, Q of x and R of x are some function of x, and then y prime here, y here, and then this entire quantity, we take the first derivative. And so the stipulation is that we have some boundary conditions on some interval between A and B. We have boundary conditions at A and B that correspond to the following equations that relate y and y prime. K1, K2, L1, and L2 are given real constants. That would be your boundary condition constants, and lambda is some parameter associated with the physical problem. So these are very common problems encountered in engineering. They're boundary value problems. The stipulation to how to solve them is at least one of these constants has to be not equal to 0, and then lambda is considered a parameter. So as an example, one type of Sturm-Liouville problem is a vibrating string of length pi, and the differential equation that determines that is given here. Now, if we have a vibrating string, we assume that it's fixed at each end, so the displacement of that string has to be 0 at 0, and it has to be 0 at pi. So it's pinned at the endpoints and vibrating in the middle, and so if you were to displace that and then let go, it would vibrate up and down, but yet it would be fixed in the center. So this is what that equation looks like. This is actually a very simple differential equation to solve, but let's look just briefly at how that relates to our generalized form. So in our generalized form, if P of x is equal to 1, and R is equal to 1, and Q is equal to 0, then this Sturm-Liouville equation becomes our equation for our vibrating string. Now, if lambda is a negative constant, then you can easily see this would be y double prime would be equal to lambda y, and the solutions are exponential functions. And the problem with that is when we look at oscillatory systems, we tend to look at modes of oscillation as eigenfunctions. So that's not really a satisfactory physical solution. If lambda is a positive constant, the solutions are sinusoids. So given that equation, we can take an educated guess that we'll have some y of x equal to a cosine nu of x plus b sine nu of x. And then applying the boundary conditions, we can see that all of our a's will equal 0 because we would require the cosine of 0 to be 0. So that means that that a would have to be 0. The second boundary condition then yields this equation, and so this equation is satisfied for a number of values of nu, all of the integers, positive and negative, and 0. So for nu equals 0, y is equal to 0. If lambda is equal to nu squared, basically we can take b is equal to 1, and we get y of x is the sine of nu x. So the eigenvalues of this problem are where lambda is equal to nu squared, and nu is 1, 2, and so on. And the eigenfunctions would be the sine of nu x. Now notice that this would be the sine of 1x, the sine of 2x, the sine of 3x, the sine of 4x, and so on. And that sounds an awful lot like a Fourier series, and in fact it is a Fourier series. So we basically have eigenfunctions that are sinusoids that represent the modes of oscillation of this problem. So that then leads us to thinking about, if we're saying we have independent modes of oscillation, that then leads us to thinking about what does it mean when functions on some interval are orthogonal. So what it means when functions are orthogonal is that we have some parameter, so this would be like our nu, ym of x and yn of x. And then we have some weighting function r. And so we talk about ym, yn as this particular integral where r is a weighting function. We also define the norm of y as basically if m and n are equal, then this would reduce to the following integral. If we then take the square root of that, that's the norm of y. So these are two different definitions. So orthogonal means if m is not equal to n, this integral will be 0. If m is equal to n, then the square root of this integral is defined as the norm of y. The reason it's important to have the norm of y is that we can then normalize the eigenfunctions so that they are all in the same, they all have the same vector length. So our functions y1, y2, and y3 and so on are called orthonormal if they're orthogonal and they all have a norm of 1. So if that's the case, then we can write that previous equation using the Kronecker delta symbol. So basically, this integral is 0 if m is not equal to n, and it's 1 if m is equal to n, and shorthand for that is this delta in n. Now, if r is equal to 1, then we call those functions orthogonal instead of orthonormal with respect to r equal to 1. So once again, here's your expression for what happens when r is equal to 1. And once again, the norm of y, and then it's just then the integral of y of x squared dx over the interval, take the square root. So you're noticing that this is very similar, if you're paying attention, this is very similar to the root mean square, the only difference being that because we're working with periods of minus pi to pi in this particular example, we don't have that coefficient out front. So anyway, the RMS is similar to a type of norm. So if we then look at our functions y m of x is sine of mx, and we want to form, and we say they form an orthogonal set, we can find the norm of y by doing the integration, and we get the square root of pi for that. So once we have the norm, we can then take each eigenfunction and divide it by the norm, and that gives us a corresponding orthonormal set. So once again, people like to use orthonormal sets because it puts things like, it puts functions in the same, it's sort of like a relative magnitude, so you can compare across different functions. So anyway, orthonormal sets are pretty commonly used across electrical engineering, especially in the signal processing and signal analysis field. So orthogonality of eigenfunctions in the Sturm-Liouville problems. Basically, we just define that these functions ym and ym are orthogonal on the interval a to b with respect to the weight function. And if p of a is equal to 0 and p of b is equal to 0, then you can drop certain conditions. If p of a and p of b are equal to each other, then on those boundary conditions you can set y of a equal to y of b and y prime of a equal to y prime of b. So this is called a periodic Sturm-Liouville problem, and is pretty common as well in engineering. So orthogonal functions and periodic boundary conditions are often seen throughout analysis of problems with vibrations, waves, etc. So that ordinary differential equation that we looked at earlier in the lecture, which had p of 1, q of 0, and r of 1, has eigenfunctions y is sine of m of x, where m is 1, 2, etc. And those are orthogonal on the interval from 0 to pi. It turns out that Fourier sinusoidal coefficients are not, or sinusoidal terms are not the only kind of orthogonal functions. If we look at Legendre's equation is a type of Sturm-Liouville equation where our p function of x is 1 minus x squared, our q is still 0, and our r is still 1. So in this case, the parameter is n times n plus 1, and from that theorem, it means that the Legendre polynomials, which are solutions of this, turn out to be eigenfunctions of this equation, and from that theorem, then if they're orthogonal on the interval, you have the integral of Pn is equal to 0 when evaluated from -1 to 1. So a number of these polynomials, including Legendre polynomials and Bessel functions, are orthogonal sets, and the general differential equations fall into this category of Stern-Liouville problems. So this is a common sort of classic type of problem found in engineering.